Alright, so we've heard about the harmonic series, where the terms get closer and closer and closer to zero, but the sum doesn't approach anything. It goes off to infinity. There are plenty of videos on the internet explaining why that is. Like, how could the terms of the series get smaller and smaller, but the sum not approach anything? However, we can make some changes to this series to make it something we can actually sum up and get a number. If we switch every other term to its negative counterpart, we get something really cool, the aptly named alternating harmonic series. Now, that series goes up by 1, down by a half, up by a third, down by a fourth, up by a fifth, and so on. And unlike the harmonic series, the alternating harmonic series gets closer to a number, somewhere between 0.5 and 1, instead of just going off to infinity. And we can find what that number is. Alright, so basically imagine we have a function f of x, such that f is equal to x minus 1/2 x squared plus 1/3 x cubed minus 1/4 x to the fourth, and so on. Now, it should be pretty clear that the function I'm proposing will just be the alternating harmonic series if x equals 1, but roll with me here. The point is that we have a function. Now, as you know, if we differentiate and then integrate a function, we should get the original function, right? So now let's take a derivative. So basically, if we differentiate this function, the x will turn into 1, the x squared will turn into 2x, the x cubed will turn into 3x squared, the x to the fourth will turn into 4x cubed, and so on and so on. Here, something really cool happens. As you may have already noticed, the coefficients cancel out, and we're left with some bare x terms. Now this is a series where there's an infinite amount of terms, and each term is negative x times the last term. Does that sound familiar? Well, it should. What we have here is an infinite geometric series, which is cool because we can find the sum of the series as we want to. It is widely known that the sum of an infinite geometric series can be expressed as the original term over 1 minus the ratio between each term. What that basically means is that we can take the first term and divide it by 1 minus negative x. So that basically turns into 1 over 1 plus x. Well, since we differentiated to get this result, now we need to integrate it to get back to our original function. So now we're going to integrate it, and that will equal the natural log of x plus 1, which is just an alternative representation of our earlier function. Remember how we had to plug in 1 into our original function for it to become the alternating harmonic series? Again, we also have to plug in 1. And if we plug in 1, we get the ln of 1 plus 1, which is just ln2. Can we just take a second to appreciate how cool that is? We're dealing with the really simple fractions and adding and subtracting them, and e just comes out of nowhere. Like, what? That's super cool. Like, really, really cool. But fortunately for us, our fun doesn't just end there. As a fun thought experiment, what happens if we reorder the terms? So basically, let's imagine arranging the terms like this. 1 minus a half, minus a fourth, plus a third, minus a sixth, minus an eighth, plus a fifth, minus a tenth. This rearrangement might seem random and pointless. We just proved that the sum is the natural log of 2. Why would a rearrangement of the additive terms change anything? But just bear with me. Let's look at this rearrangement. If we find the differences between each of the parentheses, we will end up with a series that looks like exactly half of the original alternating harmonic series, which is weird because we're just rearranging the terms. Did we go wrong? Did math break? No, thankfully not. While we might think of the sums of infinite series as just adding up a bunch of infinite numbers, that's not exactly what we're doing. Infinite series don't work like normal sums. When summing an infinite number of terms, we're simply finding the limit of a bunch of partial sums, or sums of the first whatever amount of terms. In different rearrangements, those partial sums will be different, even if we have the same amount of terms being added. The rearrangement above was pretty easy to calculate. Why don't we try a harder one? For example, we have 1 plus a third, minus a half, plus a fifth, plus a seventh, minus a fourth, plus a ninth, and so on, where every negative number is sandwiched by two positive numbers, the opposite of the last rearrangement. Now, it isn't really super trivial what this sum should equal to, but if we think about the series spaced out between each sandwich, we can create a new function. F of x equals x plus 0x squared plus a third x cubed minus a half x to the fourth plus a fifth x to the fifth plus 0x to the sixth plus a seventh x to the seventh minus a fourth x to the eighth plus 1/9 x to the ninth. Now, we have a function where f of 1 will equal the original series, which is useful because that is the same thing that we use for solving the normal alternating harmonic series. But it still isn't perfect. To get the answer, we need to separate the positive terms from the negative terms. Say g of x is equal to all of the positive terms summed up, and say h of x is equal to all the negative terms summed up. For now, let's just work with g of x. Just like with the alternating harmonic series, let's differentiate and then integrate. G prime of x is equal to just, well, the even powers of x. If we express that as the sum of a geometric series, we'll get 1 over 1 minus x squared. The reason we're allowed to do that is because 1 is the original term and x squared is the ratio between each subsequent term. If we integrate that, we get something a little ugly. But don't fear, we're not done yet. Now, let's do the same thing for h of x. If we differentiate h of x, we get something negative a half, 4x cubed, negative fourth, 8x to the seventh, negative a sixth, times 12x to the 11th, which is equal to negative 2x cubed times 1 plus x to the fourth plus x to the eighth, and we can express that series as a sum of a geometric series, because what we have here is a geometric series. The original term is, for example, negative 2x cubed, and the ratio between each term is x to the fourth, so our sum is now negative 2x cubed over 1 minus x to the fourth. If we integrate that, we get this. Now, we need to add those two results together. Now, if we do some algebra and work with the natural log and log algebra, we get this. Plugging in 1, we get a half times natural log of 8, which is equal to 3/2 the natural log of 2. We have rearranged the alternating harmonic series to sum to 3 different numbers. How many numbers can we sum to by rearranging the series? It turns out all of them. The alternating harmonic series is something called conditionally convergent, which means if you made all of the signs in the series plus, the series would be divergent. But for now, in its current state, it is a convergent series. Conditionally convergent series can be split up into positive and negative parts, which individually are divergent, and they have to be, because If you made the negative part positive, then the series would be divergent, and a divergent series cannot be made up of two convergent series. And if you make the negative part negative, then they're convergent. And if you subtract a convergent series from a divergent series, you'll get another divergent series. So the only way this works is that they're both divergent. Armed with that knowledge, let's imagine that there's a number we want to approach. Now, our positive series is divergent, which means we can go as far as we want to. So we can go up to that number and a little past it. So now we're a little past that number. So now we can use negative numbers to go backwards. And since our negative number series is divergent as well, we can go as backwards as we want. We can continue this process as many times as we want as we focus in on the desired number. Remember, we can do this with any conditionally convergent series because the positive parts and the negative part are separately divergent. Now, remember, this process can also work for negative real numbers too. For example, if we had -5, we could just start off with our negative series and get to -5. That's a really cool result. While we didn't prove it rigorously here, we now have an outline for such a rigorous proof. Now, let's think about what we learned here today. We can rearrange the alternating harmonic series so it can sum any real number. While that might not seem like it has any present real use, mathematics isn't really about that. It's about doing things that are beautiful for the sake of its beauty. And this is really beautiful. Thanks so much for watching. If you liked the video, please consider giving it a like or subscribing, as there's a lot more of these videos coming soon. Alright, see you next time.